I'm back. So when we left off, we were working with this one and we were trying to show that there's a zero that exists, and basically by a zero kind of know that graphically that means we've got ourselves an x-intercept between 2 and 1. And so what we did is we went and found what happened at 2, and when we plugged that in we got a 5. We already did that. And when we put in a 1 we got a negative 1. So what that means is somewhere in here, because the function's continuous, it's a polynomial function, it must have passed y equals 0. Well, y equals 0 is an x-intercept. So again, you would write on this, the intermediate value theorem guarantees a c in, I guess, the interval 2 to 1, you could even write it like that, such that the y value there would have to be 0, or there's a 0 or an x-intercept. Again, the graphical approach even makes it clearer. If you have some function that's at 5 and then it drops to negative 1 and it's continuous, at some point there you've got to hit the x-axis or have a 0. Alright? So the next topic up to date is these piecewise functions. And for those to be continuous, I think most of you have intuitively already decided. A couple of you guys said in class they have to be equal at the ends or seal up there. If not, what's going to happen is you're going to have yourself a big old gap. Because if you're doing a piecewise function and suppose one of them's heading in and it's got a limit here from the left and the other one is like that, if these aren't meeting here at this value, I've got a gap. However, if I can make them meet, you can see me moving this in here. If I could just take this one and say, you know what, the y values are the same right there, then I've got myself a continuous function. So basically what that means for you algebraically is you need to set them equal at those endpoint or points. So down here on the bottom, I've got to find a, I've got an unknown slope of this line really is what it is. That'll force my graph to be continuous. So I've got a cubic function. Generally those kind of go like this. And I've got a line and they're on a graph being separated at 1. And I've got to make sure that they meet there. So basically all I do is set them equal there. I say what will force 3 times 1 cubed to match or seal up with a times 1 plus 5. And what I get is 3 has to equal a plus 5. Or negative 2 would have to equal my a, which means the slope of my line that's going to force that to happen, or to seal up right there, is a negative 2. I'm going to go put that in blue. Now run a check on it. At 1, this one has a value of 3. At 1, negative 2 times 1 plus 5 is also 3. So I've just sealed those two pieces up. And you could go graph them both on your graphing calculator too. Maybe I'll show you that tomorrow, how to enter those piecewise on the graphing calculator. So we're just going to do a little recap here, and I have AP alert written because they tend to pop up quite often where they have these piecewise with missing parts to them. And they always give you some condition, and this one it's just telling you all it's continuous. So really what they're telling you, I've got a little typo here I want you to go add, there should be a negative 1 on that barrier. So what they're saying here is that you've got a parabola, you've got a line, and then you've got another parabola opening down. And they have to seal up at these fences on here. So what I'm going to do is, algebraically, go force them to seal at negative 1. I'm going to force that to be equal to what happens when I put in a negative 1 for x on this one. So I'd have a times negative 1 plus b. I'm going to clean that up a little bit. 1 would have to equal negative a plus b. One equation with 2 unknowns. This right now has an infinite amount of possibilities. So I've got to go seal up the other side of it. Do that with my blue. And I have to say, well, at this fence, okay, when I put this in here, I have to seal it down here also. So on the other fence, I've got my a times 1 plus b. That's got to equal my negative 1 squared. And so you just go ahead and plug that on in there. So I'm going to go do that, and I'm going to see if I have the graph on here. So I've got a plus b has to equal my negative 1 squared. And that's not negative 1 squared. It's the opposite of 1 squared. So really what I've got here is a plus b has to equal negative 1. So I've got two equations, two unknowns. So we're going to go solve that with some Algebra 1 skills. And we're going to line them up here, take the blue one, and we're going to do our linear combinations. And so I got 0 has to equal twice b, which implies that my b that was missing, that's going to force those to seal, is a 0. And consequently, because they have to add up to negative 1, or you could substitute it anywhere, my a is going to have to equal negative 1. Now that's the algebra component to it. I would like to also, again, back it up with the graph. So really, what I'm going to do here, I'll erase this part so I can put a little graph up there. I really do want you to see this one graphically. So we'll put your graph down. Alright, just like that. And we're going to structure it maybe 1, 1, 2, 3, 1, 2, 3, 1, 2, 3. Keep in mind that our fences, and again, they're not asymptotes when I do them. I told you that in class. When I'm doing them in this green dotted, it's not me putting up an asymptote, it's me putting up a fence for some piecewise functions. So, I've got a piece over here, a piece in here, a piece in here, and I had to make sure that they meet up on the fence. So when you go look at this graphically, when I am to the left of negative 1, I've got y equals x squared. So at negative 1, I'd have a 1, at negative 2, I'd have a 4, and I'd have that parabola going like that. And that would be solid because of the equality there. I'm going to even go down here and do this one next, maybe down here. The negative x squared is what happens from 1 and greater. So at 1, I'd have the opposite of 1 squared, and then at 2, I'd have a negative 4, and it's kind of a downhill parabola. And I was in search of the a and the b right here. Go back up and erase it. I was in search of this a and the b that would cause it to seal on both fences. And we said that the b was 0 and the a was negative 1. Well, let's see if that kind of matches. It has to have a y-intercept of 0, go down 1, over 1, back 1, up 1. You can see it sealing up right on those fences. So it's good graphically sound, and it's also algebraically sound. So, right down here on the bottom, my second thing I want to discuss with you is the difference between these. You're going to see these on Friday on your problem sets, and you really have to watch your approach. This means come in from the right, this means come in from the left, and this means come in from both directions. So when I'm coming in from the right of 5, I'm thinking, okay, it's like 6 and then 5.9, blah, 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 5.0000000 forever 1. So when I take a number like that and subtract 5, I'm approaching 0. The square root of 0 is 0. Looks good. When I'm approaching from the left, I'm thinking in my head 4.9999. When I subtract, I'm going to get a negative. Okay? I can't root a negative. It's illegal. So we say that the limit there does not exist. And consequently, because I am not the same limit from the left as I was from the right, the limit as I approach 5 in general as a whole does not exist. And again, backing it up with a graphical component is very helpful. And you should know that the graph of that is your, we've done these a lot where it's got that shout out to it, moved 5 to the right because 5 would spit out a 0. Looks like this. Not the best graph, but it will serve its purpose. So you can see as I approach 5 from the right, I'm going to land on 0. When I approach it from the left, there's no path even over here, so it doesn't exist. So consequently, my approach from both directions is not matching, so by definition, the limit there does not exist. So that's it for today, and we'll see you tomorrow.